We're now going to step away from integrals for a little bit and talk about sequences and series. Some of you may have had some background in this from high school, others of you may not. A sequence is an infinite list of numbers of the general form, and we usually use a sub 1, a sub 2, where those subscripts are just indicating what term number they are. So a sub 3 is the third term, a sub k is what we use to represent the general kth term. To emphasize that it's an ordered set, you will see set brackets used around a sub k at times, other times you won't. And off to the side here, we're indicating that k should take on the values from 1 to infinity. And we use positive integer inputs for this. So k is going to be 1, and then we're going to go to 2, and then we're going to go to 3, and so forth. So we're going to do examples 1 through 4, although in a little bit of a different way than the textbook does. We're going to write out the first few terms of each sequence, and then determine if it has a limit. So our first sequence is going to be a sub k, where it's defined as 1 over k. So to write out the first few terms, I would start at k equals 1, as I'm told here, and substitute that value. So I would have 1 over 1, then 1 over 2, then 1 over 3, 1 over 4, and with each term, I'm increasing the k value by 1. This creates an infinite list of numbers, and we call this a sequence. Now, usually what we are concerned about with sequences is whether they're heading somewhere, whether there is a trend in the values. So if you think about this sequence, the first term has a value of 1, the second term has a value of 0.5, the third one is approximately 0.3, then we get to 0.25, and so forth. And so we're looking for an overall trend when we say that we're looking for the limit. And the notation we use will take the limit as k approaches infinity for my particular a sub k, which is 1 over k. And if you let k increase, you'll get huge denominators. K will eventually be 10 million. It'll be 100 million. This fraction then is going to be very, very small. And it does converge to 0. And you can get that information by looking at these values and looking at what they trend to. We're also going to find you can look at a graph and you can get an idea of the trend from the graph. The next sequence, we switch the letters up. It doesn't matter what letters we use, but this time j equals 1 to infinity. For this sequence, where b sub j equals -1 to the jth power divided by j. So we'll write out the first few terms of this sequence. Again, this will continue infinitely. And we'll begin by looking at the value of each of these terms. So the first term is equal to -1. The second term, because of that even exponent, is going to become +1 in the numerator. So we have 1/2, which is the same as 0.5. Then we're going to have -1/3, so about -0.3. And then -1 to the 4th power will again be positive. So now we have +0.25. And finally, -0.2. And what you can see, the only difference between part A and part B is that the signs are alternating on every other term. But the question is still, is there a limit as we let j go to infinity for -1 to the jth power over j? To help us determine the limit, I've gone to Desmos and typed in as a function This sequence. Now you have to be careful because a sequence, remember, can only take on integer values of x, whereas the function is continuous and it can take on decimal values. So you really want to be careful here and make sure that you are aware of that fact. So if we focus on the positive x values, you'll notice that this graph is just dots because the function jumps from one value to the next value and it doesn't take on the values in between them. But we can see a general trend here where the dots on both sides do seem to be getting closer and closer to zero. So we would say that this sequence also has a limit of zero. Now, these sequences where we can find a limit, they are called convergent sequences or sequences that converge. So both A and B converge. The next sequence we're going to look at is C sub k, where that's defined to be -1 to the kth power. In this case, notice the sequence index has changed and we're starting at 0. You can start at 0, you can start at 1, and we're going to write out the first couple of terms of this one. So we would have -1 to the 0 power, followed by -1 to the first, etc. If we look at the value of these, -1 to the 0 power is +1. Then we get -1. Then we get +1, and then we get -1. And you can see that we're going to have this pattern of having positive or -1 alternating, which leads us to the question, is there a limit as k approaches infinity for -1 to the kth power? Here's the graph of the function -1 to the x power. Now keep in mind that this function is taking on some decimal values, which our sequence does not. However, as we look at what happens, this sequence does not appear to converge because it's bouncing back and forth from -1 to +1, and the values are not getting closer together. When we look for a trend, we're looking for a value that all of the values, all of the outputs are getting closer and closer to. These outputs are always staying the same distance apart. So with this sequence, this is the first time we see one that diverges because there is no one limit. For some of the terms, the limit is +1. For some of the terms, the limit is -1. So this limit, we use the abbreviation DNE, which stands for does not exist. And so this is our first example of a sequence that diverges. The last sequence we're going to take a look at is actually a very famous one, which is why we're using the letter F here. It's a sequence defined by a recursive rule. And all that means is you're going to take the initial inputs that are given and keep entering them into the rule to generate the next term in the sequence. So in other words, if I want f of n plus 2, I'm supposed to take the two previous values in the sequence. So I'm going to begin at n equals 1. When n equals 1, I can calculate f of 1 plus 2, or in other words, f of 3, by calculating f sub 1 plus f sub 1 plus 1, or f sub 1 plus f sub 2. In other words, to get the third term in the sequence, I add the previous two. So f sub 3 would equal, we're told f sub 1 is 1, f sub 2 is 1, so I would be adding 1 plus 1 to get 2. And that's the third term in the sequence. So far I have 1, 1, and 2. Now to get the fourth term, I would let n equal 2, because then we're on the left-hand side, we're going to have f sub 4 equals, and it equals f sub 2 plus f sub 3 by substituting 2 for n. We have those two values. F sub 2 is 1, f sub 3 is 2. So this time I add 1 plus 2, and the fourth term in the sequence is going to be 3. And I can do it one more time. If I now let n take on the value of 3, 3 plus 2 means I'm calculating f sub 5, which will be f sub 3 plus f sub 3 plus 1, or 4. So I add the previous two terms. I add 2 and 3, and I get 5. So if you haven't guessed already, this is the Fibonacci sequence, which is why we're using a capital F here. And again, the rule for generating the sequence is take the previous two values, add them together to get the next value. So the question is this one heading to a specific limit? As we let n go to infinity, is there a limit of value that these outputs are tending towards? Now, if you notice, we have 1, 1, 2, 3, 5. The values are increasing, and they're going to continue to do so. If we keep adding the previous two terms, we always get a bigger number. So what this suggests is, in fact, that the limit here is infinity. It's going to get infinitely large. This is another situation where we say a sequence diverges. It may diverge because there is no limit. It may also diverge if the sequence just gets larger and larger and larger without bound. It can also diverge to negative infinity. We'll look at one more initial example where we have both the function and a sequence. And the function is f of x equals sine of x over x. And the sequence is a sub k equals sine of k over k. And we're asked to plot the graphs of both. So keep in mind that for the function, f of x equals sine of x over x, if we were to make a table of values for this function, its inputs and its outputs, we would allow all real values for x. So I would let x be, for instance, -1, also -0.5, also 0, +0.5, and +1. And not only that, but it can take on any values between these values. So when I graph sine of x over x, I should be connecting the dots to indicate that the domain is all the real numbers. But keep in mind that for the sequence, a sub k equals sine of k over k, we're only going to allow k to take on positive integer values. So k could begin at 0, but you can automatically see k being equal to 0 is going to cause a problem. It's going to give us an undefined fraction. So instead, if I were to make a table of values, I would want to plug in 1, and then 2, and then 3, and 4. And these values are the only values that are allowed, not the values in between. So in other words, the word we use for that is that the sequence has a discrete domain where it's just a list of individual numbers, whereas the function is going to have a continuous domain because it's going to take on all real values. So here once again you can see I've asked Desmos to graph the function f of x equals sine of x over x, which looks like a nice smooth continuous function. Although keep in mind at 0 the fraction would be undefined, so therefore we do have a discontinuity. Now when I want to ask Desmos to graph the sequence, it does have the power to do that, and here's how. I'm going to turn this function off but let it sit there. I'm going to ask Desmos to graph points for me, and I'm going to ask it to graph the points n comma f of n, and it will use the function that I've already defined. And then in the next line, I'm going to list what values I want n to take on. I can do that by putting a square bracket and then starting at 1, 2, 3, 4, and so forth. Now, Desmos doesn't understand the dot, 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 but certainly I can do enough values so that I can start to see the trend. The function is going to be continuous. The sequence is just a series of points. But the question is, what is the limit? What is the y value that these dots are trending towards? And to see that, another thing I can do with Desmos is view the table of values for the function. I hit the gear and then the table. And I can continue generating table values and watch what happens. And you'll see that they are getting very, very small and seem to be approaching 0. So the important takeaways from the graphs of these are that f of x on the interval from 0 to infinity, and notice I did a round bracket here to not include 0 because I know there's a discontinuity there. On this interval, it is continuous, whereas a sub k is a discrete sample of f of x, meaning there's a limited number of points that are actually part of the sequence. In either case, the limit as k goes to infinity, sine of k over k, it's going to be the same as the limit as x goes to infinity of f of x, and namely, it converges to 0.